Electric force between two charged spheres. We have two small spheres with masses of 25 grams each, so the first thing you know you'll have to do is convert that to kilograms. And here they are, down here. Don't worry, we'll make the picture bigger on the next few slides. They're at the ends of two silk strings of length L equals 1.30 meter. That means the strings are insulated, so no charge is going to go up there. Both spheres are charged with an equal amount of positive charge in little q. They each make an angle of 30 degrees with the vertical. Be careful where that angle is. On the diagram, draw a free body diagram for each sphere. Determine the magnitude of charge q on each sphere. Then, due to electrical discharge, and that means some of the charge is leaving the sphere and going out into the air, the angle that each string makes with the vertical is reduced to 20 degrees. Find the amount of charge that left each sphere due to this discharge. Then, when you have theta equals 20 degrees, the right string is cut right there. That string gets cut. Find the instantaneous magnitude and direction of the acceleration of the sphere attached to the cut string, right at the instant it happens. Draw a free body diagram for each sphere. This is a pretty standard APC physics test problem, and they'll actually give you a diagram. They want you to draw on it. So this is why it's very important to bring pencils to the exam, because what if you draw it wrong at first? Then you've got a pen and it's kind of messy to clean it up. And you want to make it as easy as possible for the grader to see your good work. So please use a pencil. And typically you get a point or so for each correct vector, but they'll take points off if you put extraneous vectors in there. So for example, if for some reason you put a vector like this and said that's, I don't know, the tension vector by itself, you'd lose a point there. You also do not have to resolve them into their x and y components yet. They just want to see the full vectors. So we'll just focus on this one because it's the same on each. You've got gravity pulling it down. That pretty much works for all free body diagrams. You've got mg here. Now it's nice in this case because both masses are the same. You've got an electric force pushing you apart, okay? And that's this right over here, force of electric. And then the string is a tension force holding it up, right? Because without the tension, it would just fall down. So a correct answer to this problem, because they ask you for each sphere, you'd have three vectors drawn as so. Determine the magnitude of the charge q on each sphere. So here's where I told you to be careful of the angles, right? This angle up here is theta. So when we resolve our triangle, our vector triangle, we don't have to do it for mg, that's already on the y-axis. The electric force is on the x-axis. We just have to resolve the tension. Many times when you see a triangle problem, this is the angle you're dealing with. Not this time, so we're just going to wipe that out. We're dealing with this angle up here, and by corresponding angles, this angle theta is the same as this angle theta. So our horizontal component this time will be t sine theta, right? Most of the time you're used to that being a cosine, but you have to watch the angles. And then this would of course be t cosine theta, and you have a mirror image over here of the same vector resolution. Once you have a free body diagram, you're now able to use Newton's second law. And we're going to choose to work with this triangle. You could do this triangle set up here, these vectors. You could do either way, but you can see we have the electric force as positive, so that tells you it's pointing to the right, so we're dealing with this vector setup. So the sum of the forces in the x direction is F sub e minus t sine theta. And again, a lot of people, frankly the presentation sometimes uses this. Ft for tension, force of tension. Here we're just using a shortcut calling it t. That will equal ma, and my acceleration in the x direction is 0 because nothing's moving. Similar thing for the forces in the y direction, t cosine theta going up, mg down, that's equal to 0. Do a little rearranging and I have it just like this. Why did I set it up like this? I could have done many different ways to solve these two simultaneous equations. So think about it, then move on to the next slide. We have simultaneous equations, which means they both have to be true. One way you can do it is solve for a variable, plug it into the other one, although once you've seen a sine and a cosine, it's nice just to divide the two of them. Because what will I get? It gets rid of the tension, okay, t cancels out. Sine over cosine is tan. So I have tangent theta equals electric force divided by mg. So I'm almost there, except I don't know what Fe is. So we're going to do that next. We know to find electric force, we use Coulomb's law. So it's K QQ over R squared. We know the magnitude of each charge is little q, so we've just got two q's there. And R is the distance between the two charges. Have to do a little bit of geometry. We have the length of our string, we have this angle theta, and we want to find this distance right here. So let's just work with one of these triangles. As a matter of fact, we'll just do the left one because we haven't really been working with him at all. And we find that this side is L sine theta. But that's not the distance between the two charges. That's the distance from one charge to the midpoint. So I have another L sine theta here. So the distance between the charges is 2L sine theta. I now put that into Coulomb's law. And let's see, what did I do? I multiplied the q's together, but then I put the 2L sine theta in parentheses and then square it. This way you definitely know that's the distance. And I have this equation from previous. And I will be substituting this electric force right into there. So please go ahead and try that before we go to the next slide. It's always good to practice your algebra. So I have my tangent theta. It equals Fe over mg. Here's my term for Fe. Next thing I do, I put mg over to the right side, divide through by k, to the left side, excuse me. Right, mg comes over here, k goes in the denominator. So I have mg tan theta over k, and that equals q squared over parentheses 2L sine theta squared. I don't like this, right? We've got a horizontal line here, horizontal line here, so I just cleared that out. I solve for q squared, and then I get q is equal to this term right here. Since we were given numbers, they want a numerical answer this time. So here's my value for q. And let's see, could we have cleaned that up and put people under the radical? I'm not sure. It wouldn't have given us much, right? Because I could have put this under here. I would have had sine squared theta times tan theta. Tan is sine over cosine. Nah, it doesn't look like it gets too clean. So we'll just stay there. We will put in our values. And notice right there, we change grams to kilograms. We use 9.8 meters per second squared for G. The AP exam does say use 10. So I'm kind of torn on that. It isn't 10. It's 9.8. It's kind of like an important number. But frequently the math will be easier if you use 10, especially if they're multiple choice. Sometimes you use 10 and you get nice even numbers. But either way is absolutely correct. I chose to use 9.8 here. Make sure you put the units in. And at the end, we have the charge on each one of these spheres is 5.15 microcoulombs. Due to electric discharge, the angle that each string makes with the vertical is reduced to 20 degrees. So what we have is the two strings are now something like this. They got closer together. And why is that? Well, you lost some charge, so Coulomb's law, which is KQQ over R squared, smaller q, the force is smaller, and they shrink in. They get closer to each other. There's not as big a force keeping them apart. So we're going to use the same solution we just did. Everything works. That's the advantage of doing all the algebra first. We can still use that algebraic solution with the sine and the tangent, but we'll just plug theta is equal to 20. That will tell us the charge we have at 20 degrees. And then all we have to do is subtract that from the charge we had at 30 degrees, and that'll tell us how much charge left the sphere. Just to advertise again, that's what the sheer beauty is of solving everything algebraically first, because then I can put whatever numbers in I want, whatever the situation is changed to. So I'm going to find my new charge. I'm going to call it q prime, and the length of the string is the same, the mass is the same, g is the same, k is the same. We just have a different angle. So when we put that angle in, that'll tell us what charge will maintain these two spheres at those 20-degree angles. So I plug the numbers in, I get an answer, and I find that the charge that will maintain that configuration at 20 degrees is 2.80 microcoulombs. Now the question, make sure you read the question. It says, how much charge left due to the discharge? I know originally at 30 degrees I had 5.15 microcoulombs. Now I only have 2.8 microcoulombs left on the sphere. Where did the rest go? It discharged into the air, and that's the answer I want. So it's going to be 5.15 minus 2.80 microcoulombs, and I get 2.35 microcoulombs of charge left the sphere. It's not left on the sphere, it went out into the atmosphere. Final part of the problem. One of the strings is cut. So let's make it this cut. We've been working with the right-hand string. When it's cut, what force goes away? Well, the tension force no longer exists. So I have a horizontal force due to the electric force and mg gravity going down. Now, the reason we ask what's the instantaneous force, once this charge starts moving, Fe is going to decrease, right? This is going to get farther away from that charge. This will stay the same, but your acceleration will be constantly changing as the charges move apart. So we're calculating the instantaneous one. We're assuming it is right there at that split second. What happens? Actually, what we have here is a simple projectile motion problem. But let's look at my acceleration in the y direction first. That's typically the simplest. It's the force of y divided by m. So that'll be mg over m. It equals g, 9.8 meters per second squared. And you probably didn't have to do all that algebra. You know that a freely falling body will always have an acceleration of g in the downward direction. Again, assuming no friction. Now I have to calculate the acceleration in the x direction, that instantaneous acceleration. Well, I know the force. We calculated the electric force, back a number of slides. It was this guy right here. And it's that force divided by the mass. I simplify it as best I can, plug the numbers in, and I get the acceleration in the x direction is 3.57 meters per second squared at that instant when the string breaks. All that remains now is to use some Pythagoras and trig or geometry and figure out the total acceleration. So let's do the magnitude first. Here's our two accelerations. This is the y direction, this is the x direction. I've got a total acceleration, which is going to go like this, right? Because that's in the same direction as the net force. Let's just put a theta here. So the magnitude, that's the hypotenuse of the electric force in mg, 3.57 squared plus 9.8 squared, and I get a total acceleration of 10.4 meters per second squared. I then want to find that angle theta, right? Because if I want to find acceleration, acceleration is a vector. I need a magnitude and a direction. You probably won't get a lot of credit if you just say, hey, it goes off to the right at an angle. Pretty sure they want the angle here. So that's going to be the arctan of AY over AX. Plug the numbers in, and theta is equal to 70 degrees.